Lecture 6-1, Instantaneous Power. Students should be reading section 10.1 of their textbook in order to supplement this lecture. Upon completion of this lecture, students should be able to briefly and clearly explain instantaneous power, average and reactive power, and solve AC circuits for the instantaneous power. Understanding how electric power is produced and supplied is very important for all engineers. It is the rate at which work is done by an electrical component. It tells us how much heat will be produced by an electric furnace or how much light will be generated by a bank of fluorescent tubes. It is also important to know the power rating of a device so that we can ensure that the rating is not exceeded. When voltage and current vary with time, their product is instantaneous power, P of T equals V of T times I of T, and it has units of watts. And we can represent that as V sub m cosine omega t plus theta V minus theta I times Im times cosine omega t, or V sub m I sub n cosine omega t plus theta V minus theta I times cosine omega t. Using trig properties, we can rewrite the instantaneous power as 1/2 Vm Im cosine theta V minus theta I plus cosine theta V minus theta I times cosine 2 omega t minus sine theta V minus theta I sine of 2 omega t. When we plot the instantaneous power, we get the following sinusoidal shape, which has an offset of 1/2 Vm Im, and notice that the offset from the zero axis is 1/2 Vm cosine theta V minus theta I, and the amplitude from that value is 1/2 Vm Im. From the instantaneous power relationship, it can be observed that the power frequency is twice the frequency of the voltage or current. Also, the power may be negative for a portion of each cycle, which implies that energy stored in an inductor or capacitor is being released when P is positive, energy is being stored, when P is negative, energy is being delivered. The instantaneous power can also be rewritten as P of T equals P plus P cosine 2 omega t minus Q sine 2 omega t, where the average or real power is P is equal to 1/2 Vm Im cosine theta V minus theta I in watts. The average power describes the power in a circuit that is transformed from electric to non-electric energy. Examples of devices that convert electric energy to thermal energy are stoves, ovens, toasters, irons, water heaters, electric clothes dryers, and hair dryers. This is what is usually meant when we just say power. Its symbol is P, and the units are watts, kilowatts, megawatts, etc. It is the rate at which electricity is being converted into another form of energy. In other words, it represents the useful work that is being done by the circuit. It is a scalar quantity. The reactive power is Q is equal to 1/2 Vm Im sine theta V minus theta I. The units are vars. Reactive power is associated with the energy stored in an inductor or capacitor. This is the energy that is exchanged back and forth between the source and the load, and it is not converted into non-electric energy. This does no useful work, but represents stored energy oscillating between the source and the inductive and capacitive elements. Its symbol is Q, and its units are volt ampere reactive, or var, kilovar, or megavar. Dimensionally, vars are the same as watts, but we need to use a different name to identify which kind of power we are talking about. Like real power, it is a scalar quantity. So a few reminders: instantaneous power oscillates at twice the applied frequency. It has a mean value that determines the amount of work done over a specified period of time. The instantaneous power in a resistor is never negative. Resistors always consume power and never return any to the source. The instantaneous power in pure inductors and capacitors has an average value of 0. All of the energy drawn out of the source in one half cycle is returned in the next half cycle. When calculating the mean value of power, always use the RMS values of voltage and current. The RMS values are the peak value divided by root 2. All values quoted in product specifications are RMS unless stated otherwise. Average power is the product of the voltage RMS magnitude, current RMS magnitude, and power factor, where the power factor is the cosine of the angle between the voltage and the current. So here we have a purely resistive, purely inductive, and purely capacitive circuit. Notice that the purely resistive circuit is real power, the purely inductive circuit is reactive power, and the purely capacitive circuit is reactive power. And all of them have a sinusoidal input. So now, if you plot the voltage, the current, the average power, and P of T, you'll see for a resistor that the voltage and current are in phase, and P of t is double the frequency, and the average power is a non-zero value. Next, if you plot the current, the voltage, the average power, and P of t for an inductor, you see that the average power is 0, and that P of t is double the frequency of the voltage and the current. Similarly, for the capacitor, if you plot the voltage, the current, the average power, and P of t, you see that P of t has double the frequency, the average power is 0, and voltage lags current by 90 degrees. Remember, that represents ice, and current lags voltage by 90 degrees, that represents Eli. So here's our phasor diagram again as a reminder, where the first one is V equals I times R, where the voltage and current are in phase. And then we have the second one, V equals J omega L times I, where the voltage leads the current by 90 degrees, or current lags voltage. And then we have I equals J omega C times V, where current leads voltage by 90 degrees. And recall that that's Eli and ice. So the resistor has an average power, P greater than 0, and the reactive power, Q, is equal to 0. The inductor has an average power, P equals 0, and the reactive power, Q, is greater than 0. And the capacitor has an average power, P is equal to 0, and a reactive power, Q, less than 0. So now the instantaneous power for each of these becomes, for the resistor, P of t is P plus P cosine 2 omega t. For the inductor, P of t is equal to negative Q sine 2 omega t. And for the capacitor, P of t equals negative Q sine 2 omega t. Example 1, what is most approximately the average power dissipated in the following circuit? We're going to assume Vm for the source, or V peak, unless explicitly stated as VRMS. So the source is 115 with an angle of 40 degrees. And the first thing we're going to try to do is to find the input impedance as seen by the voltage source. So we are going to simplify this circuit down to the voltage source and the impedance. So when we do that, we are going to have 1 plus J2, and then 5 plus J, 2 plus J6, and negative J8 in parallel. Recall that the power is 1/2 VMIM cosine theta V minus theta I. So here we're going to draw our voltage source with the value of 115 with an angle of 40 degrees. And that's in series with 1 plus J2 ohms. And then when we combine those components on the right in parallel, we get that the impedance of 5 plus J in parallel with 2 plus J6 in parallel with negative J8 is equal to 3.862 plus J ohms. So next we're going to define a clockwise current, and we are going to find the current through the loop, which is I is equal to V over Z. So 115 with an angle of 40 degrees divided by 1 plus J2 plus 3.862 plus J ohms, and we get that the current through the loop is 20.13 with an angle of 8.32 degrees, and the units are amps. That represents theta I, and the magnitude is 20.13 for the current. So P is equal to 1/2 times 115 times 20.13 times the cosine of 40 minus 8.32. So the average power for this circuit is found to be 983 watts. Notice that if the source had been given in RMS values, the answer would have been double 983, which is 1966.